Today we're going to translate a simple object-oriented example from Java to C++. Specifically, we'll look at encapsulation, inheritance, and polymorphism, the three pillars of object-oriented programming. So here's the simple example. We have an abstract base class animal with a name. That name is initialized in the constructor via assignment from the parameter. And since Java references can be null, we require at runtime that we don't want a null reference. Okay, then we have a pet method, which simply prints to the terminal the name of the animal, followed by a says, followed by some sound, where sound is an abstract method, which means the subclasses have to override the sound method. Okay, so here is the first subclass, cat extends animal, which means the field and the methods are inherited, but we have to provide our own constructor, which simply delegates the parameter to the animal constructor. So this is the syntax for saying I want to call the constructor of the base class. Okay, and the sound method is overridden in such a way that we always return meow for cats. And in the second subclass for dogs, we return woof instead of meow. That's the only difference between cats and dogs in this example. Okay, so let's look at the main method. Here we have a variable of type animal, which we initialized with a reference to a cat object. Then we call the pet method, and then we assign a reference to a dog object and call pet again. And we would expect to see something like Adam says meow and Alex says woof. Let's see if that already works. Yeah, Adam says meow and Alex says woof. And the other output is triggered by the following example. Here we have an array list of animal where we add a cat and a dog into the array list, and then we iterate over the array list, and for each animal that we see in the animal list, we call the pet method. That's why you see Kitty says meow and Becky says woof, because those are the two animals in the list. And note that any compiler could be smart enough to figure out that this will always call the cat method, that this will always call the dog method, but here the compiler can't know that. Sometimes it's the cat method, sometimes it's the dog method. So this example isn't particularly interesting, right? We could have simply had two variables of type cat and dog, but here this is really interesting. Okay, so that's the Java example. Here's a first attempt of a translation from Java to C++. So our base class animal has a name, which is private, even though I didn't specify private. That's because all members of classes are private by default, until we hit a public label, which makes everything after it public, and or a protected label, which makes everything after it protected. You can also have private labels, and you can have as many of those labels as you wish. You can mix and match as you see fit. Okay, here we can see the constructor for animals. The parameter is a const string reference because we want the parameter to be able to read from the original. We don't want the parameter to be a copy of the original. Okay, and then we simply assign the parameter to the field. Note that assignment for class types like string simply means we call a special method operator assign, which looks like this. So assignment is just a syntactic sugar for this method call. And of course, every method call can only work if the object is already initialized or constructed. And indeed, the compiler silently inserted that name should be initialized by the default constructor. This is called the member initialization list. And if you don't mention a member of class type, then the default constructor is used. Of course, this is a bit wasteful. So basically, first we create an empty string and then we replace it with another string. Why don't we simply directly initialize the field with the parameter via the copy constructor for strings, right? Then we don't need the assignment anymore, and the body is completely empty. That's the idiomatic efficient way to initialize fields with parameters. Okay, then the destructor simply prints to the terminal that the animal with his name is about to leave this earth. and inside the pet method we call the sound method, which isn't abstract for now. We'll make it abstract later. So for now it simply returns some default dummy string, override me. Okay, here we see the first subclass. So this syntax is basically the extends from Java. Cat extends animal, which means we inherit the fields and the methods. And just like in Java, we have to provide our own constructor, which simply delegates to the base class constructor. So this is the C++ equivalent of the super syntax. So we can use this colon syntax for fields, but also for the base object of our derived object, if you will. Okay, cool. And then inside the sound method, we simply always return meow for cats. And inside the dog class, we always return woof for dogs. Just like in Java, the only difference between cats and dogs is that cats say meow and dogs says woof. Okay, then let's look at the main function, what happens down here. So here we have a variable of type animal, which is initialized with the cat object. And later we replace that or assign a dog object to the animal variable. And we pet the cat and the dog. What happens if we compile this program? So first of all, we get two type errors, which basically state that you can't initialize an animal with a cat because cats are not animals, and you can't assign a dog to an animal because dogs are not animals. So when you write this colon here, this only gives you inheritance. I want to inherit the fields and methods, but it doesn't give you subtype polymorphism. If you want to state that a cat is an animal, you have to write public before the base class. This is called public inheritance, and that's a distinction that doesn't exist in Java. Okay, so at least now the program runs, and you can see that this temporary object is copied into A, and then it is destroyed, and then the Adam says line is outputted by this line here. Basically, we pet the copy of Adam, then this dog, after it is assigned to A, is also destroyed, and here we pet the copy of Alex, and when A goes out of scope, the copy of Alex is also destroyed. Okay, so that's clearly not what we wanted. We didn't want to copy cats and dogs into animal variables. What we wanted this variable to do is to refer to a cat first and later to a dog without those weird copies. And the most lightweight and most error-prone syntax is to use C pointers, which we denote with a star. Then we have to allocate not temporary objects on the stack, but objects on the heap. We do that with a new keyword, just like in Java. And then the dot changes to an arrow. Okay, what happens now? Okay. Now these temporary object destructor calls are gone at least, but now the leak sanitizer detected 2 memory leaks. That's because every object that was allocated via new has to be deleted. We do that with delete A down here and delete A down here. So this line deletes this cat Adam, and this deletes this dog Alex. Let's see. Okay, at least those nasty memory errors are gone. Okay, so we still don't get the strings that we want, and notice also that we only destroy animals and we don't see the destructors for cats and dogs. We'll fix that later. Okay, so apparently the call to pet, of course, calls this method. There's only one pet method. And this call to sound seems to ignore the overrides in cat and dog. Let's see. We can even be more specific and say, we really, really want this to be an override. We do that with a contextual keyword at the end of the method header. And now C++ should help us and say, hey, here you told me you want to override a sound method, but you can't really do that. Sound can't be overridden. That's because methods are dispatched statically by default in C++. So it basically means the compiler will already resolve that this call will always land here. So an optimizing compiler will probably inline this string right here. Okay, and if we want to enable overriding or virtual dispatch, we have to write the virtual keyword, and then we should see something more sensible. So here you can see that Adam says meow and Alex says woof, finally. Okay, but still, you can see that we only see the animal destructors, not the cat and dog destructors. And that becomes a real problem if cats and dogs have additional members. Let's say that cats have 9 lives. Now a cat requires more memory than an animal, and then we should see an interesting error. Okay, so what is the error telling us? Basically, it tells us that this new cat allocated 48 bytes on the heap, but this delete only deallocated 40 bytes from the heap. So basically from this point on, the heap is probably completely messed up. So everything can happen from now on, basically. This is called undefined behavior. Okay, so while this call to patch or this call to sound was dispatched dynamically, or we got a virtual dispatch, we didn't get this virtual dispatch for the delete call because the destructor in animal is not virtual. Right? If I make the destructor virtual as well, then we should also see the other destructors, and the memory leak should be gone. Right? Here you can see it. Here we destroy Adam, first the cat part, then the animal part, and here we destroy Alex, first the dog part, then the animal part, and the memory errors are gone. That's beautiful. Okay. But of course, manual new and deletes are very error prone. For example, I could delete the object too early, or I could delete the object too well, or too late, or I could do it twice. So this is almost never what you want. What we want to have instead is a pointer that when the pointer is destroyed or goes out of scope, it immediately or automatically releases the object that it points to. And we do that in C++ with a standard unique pointer, which has exactly the properties that I just explained. You don't need the delete anymore. And also, it's called unique pointer because no 2 unique pointers can point to the same object. Okay. Right, now we get tons of error messages. That's because there is no implicit conversion from C pointers to unique pointers during initialization, and also not during assignment. So we have to replace this syntax with a direct initialization to tell the compiler this is really what we want, and we have to replace the assignment with a call to the reset to tell the compiler, yes, we're really sure that's exactly what we want to do here. Okay, and you can see Adam and Alex are destroyed automatically. So Adam is destroyed or deleted when we call reset. Right, you can see it immediately before Alex says woof. And then Alex is destroyed when A goes out of scope. So that's really cool. Okay, nice. Okay, maybe now let's look at the abstract part. So this override me is never returned anymore. We don't really want this method body anyway. So how do we make an abstract method? So unfortunately, we can't simply write abstract. So the standardization committee chose not to introduce a new keyword. Instead, we still have to use the weird syntax from the 90s, which looks like this, right? This is basically the equivalent of an abstract method in C++. And once at least one method is abstract, the class is abstract as well. So you can't mark it as abstract. That's just implied by the fact that we have one abstract method down here. Okay, cool. Now maybe let's get rid of this example because it already creates a lot of output on the terminal, and let's concentrate on the array list example from Java. How would we do that in C++? So we can make a vector of unique pointer to animal, like this. Okay, and then we can try to push back a new cat. I think it was kitty in the Java example. And I didn't specify the vector. Let me do copy paste, that's a little faster. Hopefully. Yeah. And a new dog. I think we named it Becky. Okay, so this should already give us some error messages. Oh, I forgot the T. That's a silly mistake. Okay, and now basically this is the same error. There's no implicit conversion from C pointers to unique pointers. And the simplest way to fix that is to say standard make unique of cat and standard make unique of dog. That's a factory function for making unique pointers. Yeah, and that does what we want. We forgot to iterate over that vector. How would we do that? Let's make it a little more simple to read. So there's also a for loop in C++, just like in Java. So we could say unique pointer animal of animals or in animals, and then we can pet the animal through the unique pointer. That should also give us an interesting error. There we go. Use of deleted function copy constructor. Okay, so I already told you unique pointers are unique, so you can't copy unique pointers because that would violate the property that no two unique pointers share the same object. And this syntax says for every element in this vector, make a copy into this variable. Right, so just like in parameter parsing, if you write it like this with a normal value semantics, you will get a copy. We don't want a copy. We want to read from the original, and then everything should work again. Okay, and if you read this code from top to bottom, at this point you probably understand that the element type is a unique pointer of animal, so you can replace it with auto. The compiler will infer the correct type. Okay, cool. Yeah, so that's basically all there is to it. So then maybe let's do a quick recap. What did we learn about encapsulation, inheritance, and polymorphism? So first of all, encapsulation. So all class members are private by default, and you can have public, protected, and private labels to specify what the following members should, what its visibility should be. Okay, then the inheritance part. So here we say cat inherits from animal or extends animal, which means we get the fields and methods for free. Okay, and then the polymorphism part was the hardest one. So first of all, we have to publicly inherit from the base class. Then we have to make our the methods that we want to override, we have to make them virtual, and the abstract methods, we have to make them abstract with this funny equals 0 syntax. And the rest of this lecture was basically spent on memory management, so please don't use new and delete. Instead use unique pointers. That's how you declare them basically. That's how you create them. And if you want to iterate over a container of unique pointers, you can't iterate by value, you have to iterate by const reference, but that's basically almost always what you want to do anyway, right? If you want to iterate over a vector, why would you want to copy the elements just for the purposes of iteration? That doesn't make much sense. So I basically almost always use this idiom to iterate over a collection. Okay, so that was basically all there is to it. There's one little thing that I also wanted to mention. So why did we use protected down here? In Java, we couldn't use anything else. In C++, we can also write private down here. That works perfectly well. So it's possible to define a private virtual method and then override it in subclasses. That's an established idiom in C++. So Herb Sutter has written an interesting article about that. I just wanted to mention it because you will probably see it in your C++ career. Okay, so that's all for today. Thank you for watching.